One of the big problems of neural networks is how to generalize. And this generalization can be thought of as a domain generalization. Across different modalities, for instance. And here, all these ideas are coming from this paper. Some of them are not very explicit, so we don't know exactly what they mean unless you go deeper into the papers. But I think it is important to get exposed to these ideas. So this domain generalization can be done at multiple levels. Some of them have already appeared along the course. So the first one is data level. So manipulating the input data, the feature level, so that we have a shared feature representation that is useful for multiple tasks, or model level. So somehow having a learning strategy or a model architecture that help us to uh, to learn better and to generalize to other input datasets, and the analysis level that we will keep for later. So at the domain level, here we have a minimization between, so H is our neural network, so X goes through H, and then we try to mimic or to produce some data Y, and there is a loss between our predicted Y and the true Y. So this is the standard optimization of supervised problems. And here what we do with this domain generalization, we can augment the input data, and then we can add some laws related to the augmented domain. So for instance, here this data manipulation can be intensity normalization or intensity changes, or histogram matching, global color normalization. So we may adapt the different domains, especially with images, for instance, so that the images of one domain look like the images in the other domain. We can do that in some surrogate space, like a Fourier space or an input or a learned dictionary. We can also apply data augmentation, so random flipping, rotation, shifts, scaling, noise, intensity scales. We can do this adversarial based data augmentation. We have seen the adversarial networks, so the synthetically generated images can be used as data augmentation, generative models, where some of the problems can be rather, or some of the strategy can be rather specific. So for instance, in MRI, magnetic resonance imaging, where we have multiple ways to collect the data, we can use patches coming from the different kind of domains to have some kind of composite images, so the network cannot be very specific to the specific modality that we are training on. So all these strategies, they work at the level of data, so manipulating data and trying to get the same labels. Another possibility is to act at the level of features. So the idea is to have a common feature representation that is shared across multiple domains. Multiple domains, we have to think of domains like this one, in this sense, where we have multiple modalities getting input vectors for the same object, and or adapting the feature extraction on the fly during the inference. So for instance, here we have decoupled the two kind of feature extractor F, and then these features that have been extracted, they are used to produce an output that resembles Y. So that can be, so if we call these features f of x z, then we can normalize, or we can, for instance, if we have xi, xj coming from different domains, but they refer to the same object, we may force that the internal representation of fxi, fxj, they look similar, or some information theoretic approach. So trying to get the features such that the the latent space representation for a given task and for a given domain, they are similar. This contrastive, we can see that this f is the feature extractor. So the features coming from the same object should be mapped to a similar location, while all the other features coming from other objects, they have to be the way, or we can impose some variational knowledge on the latent space. So for instance, that the latent space should resemble some prior, or we can be explicit, so we have some activity or some task to perform, and this task that is C, so we have a loss function that depends on C. There is also another approach that is called disentanglement. So in the disentanglement, a part of the latent space representation is specific for a given task, while some other part is general and it is shared across domains. So for instance, we may minimize the information carried by or the common information from the task part of the latent space representation and the general part of the space of the latent space. So that means that the information cannot go, so they cannot have information that is shared. So that means that the task, the information that is learned from the task has to be independent from the information, general information from the domain. Yeah, all these ideas, they have already appeared here, so they are the same. Then we can generalize by changing the learning strategy. So for instance, we can use a part of the data to learn some weights. This part is called the meta learning, and then we use the learned weights to initialize the weights for another task. So the task dataset is smaller than the meta dataset. So the meta dataset is kind of general task that we are learning, and then we use those weights that we have learned for the general task to initialize the weights for the specific task. Or we can have this self-supervised learning, in which we first learn a helpful representation of the input data, so for instance, kind of autoencoder if you want, and then you use the learned features to learn the task that you have to learn. This adversarial learning learn the task with perturbations of the input data. Then we can work at the level of model. So for instance, ensemble learning learns multiple networks, each one on a different subset of the data or with different architectures, and then you combine the predictions of the different experts. Model distillation that we have already seen. So you learn a teacher network, and then this teacher network, or there is a student network that has to learn the teacher output. Distributed learning, that you learn separated networks, all of them with the same architecture, and then you combine the weights of the different networks at the end. Or this distributionally robust optimization, so that is learning in the worst case scenario. So typically we normalize this expected loss according to some distribution, But then if we have multiple distributions, multiple scenarios, we may learn or we may try to learn the kind of minimax. So minimax is you take the loss, the expected loss under the distribution Q, you take the maximum of that or the supremum of that, meaning that in the worst case scenario, this is the loss that we will have, and then we try to minimize the loss in the worst case scenario. So this would be it for the domain generalization. Remember, all this is coming from this paper. If you are interested in the details, you should go to the paper.